Okay, this is a quick video about what happens when ropes have mass. If you've done physics problems before, you know they always say a massless rope does this, a massless rope does that, and we always say, don't worry about the mass, don't worry about the mass. Well, let's worry about it and see what happens. So we'll take a look at what happens when ropes have mass, and we'll learn about something called a catenary, and maybe we'll even learn something about medieval architecture along the way. So here's a rope. Nothing too exciting going on. Let's just keep the rope massless for now and just refresh ourselves about what happens. If I throw a box on this and I'm interested in finding the tension in the rope, the thing I do is the thing I always do, which is I make a free body diagram. In this case, the tension from the rope points up, the weight points down. Those two cancel because the box is in equilibrium. In other words, the acceleration is 0. And so in that case, the tension is mg. So much for that. What happens if I add another box? Well, now I have 2 boxes and 2 ropes, so I need more than one free body diagram. I have 2 free body diagrams, but notice this time, this box has one tension pulling up and a tension pulling down, and that is reflected in my free body diagram. So my equation becomes a little bit more complicated. I now need to find out T2, but that's easy. I can just look at the equation of motion for the other block and I can do some substituting and blah 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 blah. What happens if I add a third, a fourth, a fifth, and so on? I'm just going to repeat this process over and over again. And so let's just say for the nth block, our strategy is to make a free body diagram that has one of the ropes above it pointing up, one of the ropes below it pointing down, and the mass also points down. So you get the sense that this tension that points up obviously has to do more work than the tension that points down because it also has to balance gravity. Okay, so in general, if the rope is in equilibrium, then that's the equation of motion reduces to that. It just says that as I climb the rope, the tension increases. Okay, but what's a rope? A rope is just a bunch of little boxes connected by infinitesimal little invisible ropes that connect themselves. And so in this case, I'm just going to apply my formula when I had big bulky boxes to each one of these little boxes. And I'm going to rearrange it a little bit so it looks like that. And there's just one other thing I'm going to do. I'm going to call M dm. Why am I calling M dm? Obviously because I want to do some calculus, but conceptually, each one of these has a really tiny mass. Okay, so how do I figure out what dm is? What do I do there? Well, I say, look, the bottom of the box is at y, the top of the box is at y plus dy, and so dm is mass per unit length times length, and another way to say that is that it's the mass per unit length times a little tiny bit of length. In other words, you get an infinitesimal bit of mass by examining an infinitesimal bit of height. Okay. Now, instead of saying Tn and Tn plus 1, t is now a continuous function. So t can be evaluated up here, and t can be evaluated down here. The procedure's the same. I've just switched from discrete boxes to a continuous function. Okay, and so if I look at this, I do a little bit of rearranging, and if you look at this, hopefully the alarm bells in your head are starting to go off. And you might say, oh, that looks like the limit definition of a derivative. Because it is. It's just a derivative. And the good news is, we know how to undo derivatives. You do an integral. Holy Toledo, that was easy. Look at that. We just derived a formula for the tension in a string that has mass. What does this say? It says a couple of things. Number one, it says that as you go up, the tension increases. The tension increases. Okay? So why is that? It's because you can think of this point having to support everything beneath it, and there is more mass beneath it, okay? The other thing is, what's this guy C about? What, shouldn't we figure that out? Well, C, this math is really powerful, and it understands that you might want to hang additional stuff from it, and in that case, if you did, okay, fine. C would be that constant, and that gets added on top of everything else, right? Now I want to do a really weird thing. I want to turn off gravity. I'm not turning off mass. Everything still has mass. I just don't want forces associated with that mass anymore. So let's turn it all off. In other words, set G equals 0. What happens? What happens in that case? Well, you just plug in 0, and T of Y is now 0, right? Okay, so that's the same as if there were no block. There's really no point in having the block there. But you might say, wait a minute, does that mean that a rope can't have tension? No, of course a rope can have tension. I just tug on it, and what I've now found is that that constant from earlier is F. Now I'm back to the case where the tension everywhere in the rope is exactly the same. I'm sure you'd believe me if I just said you could turn it on its side. It seems reasonable. It's the same thing. The only reason up down is different than left right is because of gravity. But remember, I turned off gravity. And so since I'm tired of pulling on the rope, I'm just going to attach it to another wall. That way it stays where it is. This rope has a certain amount of tension in it. Think of it like a guitar string pinned at two places. I could always tighten it if I want to, but those two places are pinned together. Okay? Now here's the question. What happens if I turn gravity back on? I've pinned it between two walls. It already has some constant amount of tension in it. What's going to happen? Well, I made a little sim to show you. I think you already know the answer, right? You've hung a string before. You know what it does, right? It's going to fall and it's going to make some kind of a U shape. There's a couple things I actually want to point out here, though, that I think are kind of interesting. Number one, if you look at the springs up here, they are longer than the springs down here. Why? Because the tension increases as we go up, just like it did before. In fact, this is a lot like the vertical string, except now I'm not allowing it to be completely vertical. It has to span some horizontal distance as well. Okay, so it's still the case that the tension increases as we go up, but now it goes up on two different sides, okay? You might look at this and say, oh my God, I already know what the answer is. It's a parabola. This looks a lot like a parabola. So if it's a parabola, let's try and prove it using math somehow. So what I did was I just lined up all those silly little boxes that we had before with the balls from my simulation, and now I'm going to draw a little curve through them, and that curve looks a lot like the curve we're trying to figure out, and now we have a continuous rope again. Okay, so what am I going to do with this? I'm going to do the same thing I always do with this stuff, and that is I'm going to make a free body diagram. I'm going to take this section of the rope, I'm going to tug it over here, and I'm going to say, look, it's got a teensy-leensy little bit of mass, so the weight points down. And then on the two ends of the rope, the big difference now is there's both vertical and horizontal components. So here what I mean to say is that the tension is a function of y. Tension's a function of y. This is the tension at y. This is the tension at y plus dy in the y direction. This is the tension at x plus dx in the x direction. The thing about the x direction is we already know that it has to be constant because I haven't changed anything in the vertical direction. These two, the tension in the x direction points this way. This is t of x plus dx. This is t of x. Those have to cancel if this thing is at rest. So none of that has changed. That doesn't impact us at all. The thing that does change, obviously, is that we have to balance the weight now. So if I set up my equation of motion in the up-down direction, I say that the difference in tensions has to somehow balance the amount of weight there, right? Okay, so how do I figure out what to do with this? Because I don't want tension. I want to find the shape, right? So one thing to observe is that the tension points along the string. So actually, the direction that the tension arrow points is the same as the slope of this curve that we're finding. In other words, the tan of theta, if I call this theta, the tangent of theta is dy dx. One thing to note really quickly, it'll come up again in just a second, is that notice that that angle changes. Down here it's phi and up here it's theta, and those angles are different. Not only is the tension a function of where I am, but the slope of this curve is a function of where I am. So if I wish to include all that information, one thing I can say is let's replace dy by dy dx times tx. What's tx? F, always. That means that I can replace this with dy dx evaluated at x plus dx, and I can replace this with an f dy dx evaluated at x. It looks a little fancy what I'm doing here, but honestly, it's just a quick substitution. This side probably looks very puzzling to you, but here's dm, and dm is the amount of mass. Ooh, I left off a g. Don't tell anyone I left off a g. But this is lambda dl. In other words, it's still mass per unit length times a little bit of length, only now my length is more complicated than before. I'm not going up, down, I'm not going left, right, I'm actually doing both. I move a distance dx this way, I move a distance dy this way. I know it's curvy, but your calc professor will tell you that in the limit that dx and dy are very small, the length of that thing is dx squared plus dy squared. So this whole term is dm. Okay, so if I go down again, I'm also missing a g here. Don't tell anyone. So if I go down again, what I've done is I've factored the dx out of this and then brought it over to the other side. And the reason I did that is because if you look at this side, it should look suspiciously like what we had before when we had vertical rope. It's the difference of a thing, difference of a function divided by the dx, and so that looks like another derivative. So it's the derivative of dy dx, which is a second derivative. And since it's really annoying to have to write things in this notation, I'm going to switch to primes. And I'm going to rewrite the left side as the second derivative, or y double prime. And I'm going to rewrite this term as y prime squared. Okay, it looks like I finally figured out that I needed to include g, so that's good. So getting rid of this mess, what I want, the important thing is the last line. So let's just park that over there on the right. Okay, this is a second order differential equation. And you might be freaking out at this point thinking, I didn't sign up for this. I'm not ready for second order differential equations. But this second order differential equation is actually not much of a differential equation. If I make a quick substitution and I say u equals y prime, then u prime equals y double prime. And now instead of having a second order differential equation, I just have something that looks like u prime equals some number times the square root of 1 plus u squared. This is first order, it's separable, and you know that if you park this over on this side, you can actually integrate both sides. So I'm not going to go crazy doing all that. You can also just plug this into, I don't know, Symbolab or your favorite computer math tool and just solve the differential equation. But if you do one integral, you'll end up with sinh, hyperbolic sine, which sounds crazy fancy. You may have no sense of what that is. You may have no experience with it. I'll just tell you a cryptic thing and then I'll let you explore it more if you wish. But if you take the sine of a function, if you allow that function to have imaginary values, you end up in hyperbolic land, which sounds crazy. You're like, what does that mean? Imaginary sines? Actually, sines are the one that are imaginary. Hyperbolic sines are not imaginary, but I'll leave that for you for another video, another topic. So here's sinh of x. The way you integrate sinh is the same way you integrate sine. So if you do an integral of that, you end up with cosine. So the point is, we did all that work. This free body diagram actually led us to discover the shape of this thing. But I don't know, I'm kind of skeptical. I don't know, like, what are the properties of this thing? Well, let's explore it. I got another little movie. The first thing I'm going to do in the movie is I'm going to increase F. That means increase the tension. That means tighten up the string. What do you think is going to happen? Well, it should stretch outward, right? Let's see if it does what it's supposed to. That's increasing F. The rope stretches outward. Now I'm going to decrease F and increase the mass per unit length. I'm decreasing F, decreasing F, decreasing F. It's going to droop, 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 droop. That's about what we'd expect. And then, did my sim malfunction? Actually, maybe this kind of makes sense. I'll tell you what happened is that you're looking at the case F less than 0. And you're like, F less than 0? What does this mean? It's upside down. Well, if you want all of the forces to point along the direction of motion, then you end up with a shape that looks like this. And you might be like, okay, that's a weird math thing. Obviously, it has no bearing in the real world. Well, you're probably already familiar with something that does. If you've never seen this before, I'll just tell you that this is the world-famous St. Louis hyperbolic cosine building. No, it's not called that at all. It's called the Gateway Arch. And it is literally a catenary. The guy who built it, the architect, knew some calculus. He liked catenary. And the idea behind a catenary is this. The catenary is a curve that things follow when all of the forces have to point along the direction of the curve. What does that mean? That means that each of these things has some weight that bears down. It bears down. But because of the shape of this curve, all of the weight ends up being directed into compressional forces inside the material. You might say, well, what's the advantage of that? The advantage of that, and you'll learn about this when you study materials, is that materials tend to tolerate compressions much better than they tolerate stretches. So if you can design a curve that does its best to keep all of the forces pointed along itself so that you are constantly compressing the material rather than stretching it, you build very strong structures. This is actually the tallest in St. Louis. It's the tallest catenary in the world, the tallest arch. It's pretty impressive. I love this picture because look down here. That's also some sort of curved dome-like thing. We'll look at that in a second. But I also want to look at one other thing. This is an ancient Roman bridge. People have understood for a long time that curves are very good at supporting weight. They don't break. When concrete compresses, it holds its form. If these curves didn't exist and these were flat, the centers would sag and the concrete would stretch. And as the concrete stretches, it breaks. Even the Romans, who didn't know calculus, knew that curving the bottom of a bridge made it stronger. I don't claim that these are catenaries. I claim that the catenary is the optimal curve. The closer you get to a catenary, the stronger your structure will be. This is the dome. If I take that catenary shape and I rotate it 360 degrees, I end up with something that looks like this. Medieval architecture is loaded with domes. People tried to build flat churches and cathedrals, and the churches and cathedrals collapsed. People figured out that you could build a big chamber that didn't need support columns if you made catenaries on the top so that you compressed the material rather than stretching the material. If you look around you, you will see these beautiful domes everywhere. Okay, hopefully this video was more helpful than confusing.